Hello students, welcome to 8th lecture of D and F block elements. In previous lecture we discussed about lanthanoids, and today we are going to discuss about the second series of F block element, actinoids. So just like lanthanoids, we have total 15 elements to study in actinoids. But actually one of them do not have partially filled d orbital in atomic or ionic state, but still we will include that element in our study. So as mentioned here, we have total 14 elements in actinoid series, and their symbols and information are provided in the following table. But in this case, we will add our first element actinium with the other elements because of similarities. So actual F block elements will start from thorium number 19, but as we can see, we have number 89 actinium in this case as well, which do not have partially filled f orbital. So actinoids are radioactive elements, and earlier member have relatively long half-lives. The later ones have half-life values ranging from a day to 3 minutes for loratium. So the later members could be prepared only in nanogram quantities. Reason, simple thing, they are radioactive and they have very short half-life. Half-life, that means suppose our reaction is radioactive, so our simple given atoms will convert into some other atoms by radioactive process. So this conversion is one type of reaction. So exact half concentration, requirement of time to get exact half concentration of given reactant is known as half-life. As for example, suppose you have 1 kilogram of reactant and the reaction takes 30 minutes to reach at 50%, that means 500 grams of reactant. So 30 minutes is half-life of given reaction. So because of very short half-life time, these materials or these elements are hard to maintain, and this is the reason why their studies are more difficult. Electronic configuration. All the actinoids are believed to have the electronic configuration of 7s2 and variable occupancy of 5f and 60 subshell. So note here it is mentioned believed to have the electronic configuration of 7s2. That means we are not sure to have this electronic configuration for each and every element. That means we do not have enough data, or we do not have enough study or proofs regarding to their exact electronic configuration. So it is just a guess. The 14 electrons are formally added to 5s, though not in thorium. But from protactinium onwards, the 5 orbitals are complete at element 103. The irregularities in the electronic configuration of actinoids, like those in the lanthanoids, are related to stabilities of F0, F7, F14 occupancies of the 5f orbital. That means fully empty, exactly half filled, and fully filled. These are some more stable electronic configurations for f orbital. Thus, the configuration of AM and CM are Rn 5f7, that means exactly half filled orbital 7s2, and Rn 5f7 6d1 7s2. So again, in both of these elements we have 5s7 electronic configuration, because when we have 7 electrons in f orbital, it gains extra stability. So electrons will shift in f orbital. Although the 5f orbitals are resemble of the 4f orbital in their angular part and of the wave function, they are not as buried as 4f orbitals, and hence 5f electrons can participate in bonding to a greater extent. That means if we compare these elements with the previous series, that means lanthanoids, then comparatively 5f orbital is close to outermost orbitals, whereas in lanthanoids 4f orbital were comparatively very deep, or they are present inside very closer to nucleus or away from the outermost surface or valence orbitals. That's why they do not participate in bond formation. But a 5f orbital is comparatively closer to outermost orbital. It is not buried, that means it is not present comparatively deeply. That's why it can participate in bond formations. ionic sizes. The general trend in lanthanoid is observable in the actinoids as well. There is a gradual decrease in the size of atoms or M plus 3 ions across the series. This may be referred to as actinoid contraction like lanthanoid contraction. The contraction is, however, greater from element to element in the series, resulting from poor shielding by 5f electrons. So, greater the attraction towards the outermost electron, more will be the shrinking of orbitals. Now, if inner orbital provides sufficient neutrality to the nuclear charge, that means positive charge, then nuclear charge effect from the outermost orbitals will be reduced, and that's why outermost orbital electrons will move away because of less attraction, and that's why sizes will increase. But let's say our inner orbital provides poor attraction or poor neutralization towards the nucleus, and that's why nuclear charge will attract outermost orbital electrons strongly, and that's why because of charges sizes will shrink. Let's say at the center we have our nucleus which has some number of protons. This is one of the inner orbital. Let's say this is 3d orbital, and this is outer orbital 4s. So if 3d electrons provides sufficient neutralization to the nucleus, then nuclear positive charge do not reach to this outermost electron, and that's why this electron feels less attraction towards the nucleus, and sizes of orbitals will increase. So that means atoms radius will increase. But in case of lanthanoid, different thing is being observed. Suppose this inner orbital provides comparatively poor neutralization to this nuclear charge. That means nuclear charge can reach up to outermost orbitals electron in well defined quantity or in comparatively good amount, and that's why these outermost electrons feels attraction and sizes will shrink, and this is called lanthanoid contraction or actinoid contraction because of poor neutralization, and the neutralization provided by inner orbital is called shielding. Oxidation states. There is a greater range of oxidation state which is in part attributed to the fact that 5f60 and 7s levels are of comparable energies. That means they are very close to each other, and that's why they all can participate in reaction. The known oxidation state of actinoids are listed in table 8.11. So these are the known oxidation states of actinoid elements. Except one element, all the elements can show plus 3 oxidation state, and few elements having comparatively more number of electrons can show up to plus 7 oxidation state. The actinoids show in general plus 3 oxidation state. The element in the first half of the series frequently exhibits higher oxidation states. For example, maximum oxidation state increases from plus 4 in thorium to plus 5, plus 6 and plus 7 respectively in Pa, U and Np, but decreases in succeeding elements. The actinoids resemble in lanthanoids in having more compounds in plus 3 state than in the plus 4 state. However, plus 3 and plus 4 ions tend to hydrolyze. Because the distribution of oxidation state among the actinoid is so uneven and so different from the former and the later element, it is unsatisfactory to reveal their chemistry in terms of oxidation state. So that means we have few problems with the actinoid series. First of all, it is radioactive, and many of its elements have very short lifespan. That means they will quickly decay or it will undergo radioactive reactions, so they are extremely hard to study. General characteristics and comparison with lanthanoids. The actinoid metals are all silvery in appearance but display a variety of structures, and structural variability is obtained due to the irregularities in metallic radii, which are far greater than the lanthanoids. Actinoids are highly reactive metals, especially when finely divided powder form. The action of boiling water on them, for example, gives a mixture of oxide and hydroxide, and combination with most non-metal takes place at moderated temperature. Hydrochloric acid attacks all the metal, but most are slightly affected by the nitric acid owing to the formation of protective oxide layers. Alkalis have no reaction. So formation of protective oxide layer is just like aluminium. Aluminium usually do not corrode, and reason for that is when it comes in contact with oxygen of atmosphere, just like other metals, it forms oxide just like other metals. But oxide of aluminium changes slightly, and it forms a protective layer on the surface of remaining aluminium metal. That means we can say that actually oxide of aluminium acts as a protective layer on the surface of aluminium, whereas other oxides of metals are usually soft or powdery material, or they are brittle. That means they can easily removed from the surface, and that's why new surface will oxidize. But in case of aluminium, it sticks with the surface, and that's why it will protect the remaining inner atoms of the metal. So similar type of formation of the oxide layer will be seen in nitric acid situation. The magnetic properties of actinoids are more complex than those of the lanthanoids, although the variation in the magnetic susceptibilities of the actinoid with the number of unpaired 5f electrons is roughly parallel to the corresponding result of the lanthanoid. The latter have higher values. It is evident from the behavior of the actinoids that the ionization enthalpies of the earlier actinoids, though not accurately known, but are lower for the earlier lanthanoids. This is quite reasonable, since it is to be expected that when 5f orbitals are beginning to be occupied, they will penetrate less into the inner core of the electrons. So the 5f electrons will be therefore be more effectively shielded from the nuclear charge than the 4f electrons. So that means if electrons are shielded from the nuclear charge, that means they do not have proper or stronger attraction towards the nucleus, and that means we can easily remove them. If electron feels stronger attraction towards the nucleus, then they are hard to remove. So in case of lanthanoid, 4f orbital electrons are not strongly shielded. That means they form comparatively stronger attraction. Whereas in 5f orbital electrons are shielded. That means they are not attracted sufficiently strongly towards the nucleus, and that's why they are easy to remove. Hence, we have comparatively lower ionization enthalpies. And this is the reason these electrons are also available for bondings in actinides. The comparison of actinides with the lanthanoid with respect to different characteristics as discussed above reveals that the behavior similar to that of the lanthanoid is not evident until the second half of the actinoid series. However, even the early actinoid resembles the lanthanoid in showing close similarities with each other and in gradual variation in properties which do not entail change in oxidation state. The lanthanoids and actinoid contractions have extended effect on the sizes, and therefore the properties of the elements succeeding them in their respective periods. The lanthanoid contraction is more important because the chemistry of elements succeeding the actinoids are much less known at the present time. So as mentioned earlier, we have some problems with actinoids, and that's why we do not know much about them, and that's why their studies or related effects are not very important currently. And last short point, some applications of D and F block elements. So in this last point we have some of the most important uses of metals, because d orbital metals are one of the most used metals, as for example iron. So few of the examples mentioned here are already known by us, and few will be new for us. So iron and steel are the most important construction materials. Their production is based on the reduction of iron oxide, the removal of impurities, and the addition of carbon and alloying metals such as chromium, manganese, nickel. Some compounds are manufactured for special purpose such as titanium oxide for the pigment industry, MnO2 for use in dry battery cells. The battery industry also requires zinc, nickel, cadmium. The elements of group 11 are still worthy of being called the coinage metal because they were used in coin. Although gold and silver are restricted to collection items and the contemporary UK copper coins are copper coated steel. The silver UK coins are a copper nickel alloy. Many of the metals ore and their compounds are essential catalyzed in the chemical industry. V2O5 catalyzes the oxidation of SO2 in the manufacture of sulfuric acid. TiCl4 with AlCH3 thrice forms the basis of Ziegler catalyst used to manufacture polyethylene. Ion catalysts are used in the Haber process for the production of ammonia from N2H2 mixture. Nickel catalysts enable the hydrogenation of fat to proceed. In the Wacker process of the oxidation of ethylene to ethanol is catalyzed by PDCl2. Nickel complexes are useful in the polymerization of alkenes and other organic compounds such as benzene. The photographic industry relies on the special light sensitive properties of AGBR. Now some of the uses are for the old time, that means we are not using certain chemicals as described here, as for example the last example photosensitive properties of AGBR. So initially we were using the rolls in the cameras which were coated with the photosensitive material and they can capture the image, but right now we have digital cameras and printers, so we are not dependent on this last point. Okay, so few of them are still in use and some of them are not in use as mentioned here.